This morning, our first speaker is Kieran Cunha from Open Broadcast Systems. And he's going to be talking about timestamps in ST2110, what they mean, and how to measure them. And it's a very interesting topic, and I hope you all pay attention. Thanks.
Thanks, Wes, and thanks for organizing all of this. Lots of hard work going into that. So usually I do a quick company introduction. What our company does is we specialize in software-based encoders and decoders for sports, news, and channel contribution, so B2B. We're based in central London. Throughout the pandemic, used to point to my left and say Big Ben is over there, so you're going to have to imagine Big Ben is over there. There's actually probably quite a lot going on over there right now. We build everything in-house, hardware, firmware, software, everything. We build a full 2110 stack ourselves in-house. There are no third-party components entirely in our products, so we've done and MOS, timestamps, everything, you name it. Also not to be confused with the other OBS, the free web streaming product. So this presentation, there's going to be a lot to it, but I've tried to make it at least approachable to someone in the field. If you want easy, at NAB I gave a presentation called How to Explain ST2110 to a 6-year-old. Introductory, don't need to have any major background knowledge. On the other hand, if someone like Thomas Kernan or Willem was talking about PTP or ST2110 or EBU list, where they really go into the guts of it all, I've tried to put this into medium/medium hard. So I will try to introduce the topic, but there will be some maths. By all means, and also this won't try and explain everything in its fullest detail, because there isn't really that time for that. Some level of basic mathematical analysis, and we can discuss afterwards things in much more detail. So what am I going to talk about today? Why do we need timestamps? PTP, very, 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 very abridged. The RTP timestamp calculation. Timestamps versus packet arrival times, giant pet peeve of mine, not the same thing. Measurements, including some real measurements from our lab. How, at least I think a receiver should use timestamps. Others may differ, and where and why these things go wrong. So why do we need timestamps? As many of you know, in 2110, video and audio are sent as different flows, and they are raw data. We don't know what. Oh, and obviously, as a result, receivers can subscribe to only the flows they need. So audio devices don't need to subscribe to high bandwidth video or ancillary or bits they don't need. And this audio and video is raw across the network from various sources and points in time. And we need to be able to synchronize this also. That player there, when he's kicking the football, it needs to actually kick the football at the right time and make the right sound. And so what we use in 2110 are timestamps to do this. And the receiver goes and uses these to match them up. So the kick of the ball sounds like a kick of a ball, and not too late or not too early. And they really correspond to a given instant of capture. So at least for video, all packets of a video frame or field, they have the same timestamp, which is a bit different to how things were done historically. My super, super, super abridged version of PTP. So as you all know, we split audio and video up into thousands of little packets. And what we do is kind of imagine that all television started at the same time. So frames, audio was all started at the 1st of January 1970. Obviously, that wasn't the case. We didn't have a time machine to send 2110 back in the past and start. But we assume it happened. And so each video frame and field lasts a number of clock ticks. So we start from the 1st of January 1970, and that's known as the PTP epoch. And 52 years later, there is a time with that n number of frames later. That time, the beginning of said frame on the right is the PTP alignment point. I really hate that word. I wish I could come up with a better word for it. It's annoying to use. It's annoying to write PTP alignment point in code, etc. And so now, for example, if I wanted to start sending, I have to wait until the next PTP alignment point. Then I start sending my 2110, and therefore all of the streams in my facility are matched up. They start at the same time. So let's look at the timestamp calculation in RTP. And that on the right is what's known as an RTP header. And we use the PTP clock in its exact, the PTP alignment point clock value in its timestamp header. So unfortunately, it's a 32-bit value, and it has different clock rates. So 90 kilohertz clock for video and 48 kilohertz for audio. This means the video timestamp wraps after 13 hours for 13 hours for video and 25 hours for audio. So that's a bit like where an old-fashioned tachometer in your car goes round and wraps around to 0 again. That's a big problem because it needs to be thought. You have to be very careful when you do calculations. Other challenges, when you have a 59.94 stream in the US, that's not divisible by 90 kilohertz, so you have to be really careful when implementing this. So here's my maths teacher was obsessed with worked examples. We did worked examples for weeks on end. So the shoe is now on the other foot, and I'm giving a worked example, I don't know, 15 years later. So let's pick an arbitrary date, midnight, for the astronomical time. So this is time that doesn't have jumps in it, so no leap seconds. If you go back to the ST2110 for 6-year-olds, I go into what leap seconds are. And I've tried to make things simple by not using fractional frame rates. So what we do, we go and work out how many clock ticks there were. So 1,944 days times 8,6400 seconds in a day times 90,000, which is the clock rate. We divide that by 25 frames per second, and then we multiply it by 25 frames per second again. So that gives us the previous alignment point to now, or to that time point. So you get this large value here. I'll point out these values are very large. When implementing it in software, you can get overflow. I think you have to go to 128-bit intermediates. I must admit, I got this wrong several times in the process of writing this presentation, and my colleagues had to go and fix it. So it's tricky. So you take that value, and then you do a mod 2 to the power 32. So that gives you your RTP timestamp. That might be wrong, actually, but I think it's right. And it's been checked by a couple of people, but I stand corrected. It is tricky. You have to order your operations correctly, and especially more care is needed when you do fractional frame rates, because you have to have intermediates and then do divisions after the intermediates instead of before. Otherwise, you don't have the right precision, etc., etc. It's very headache-inducing. But these timestamps are not the same as packet arrival times. Most facilities will use what's known as gapped mode, and there's plenty of presentations that talk about the intricacies of gapped mode, where historical blanking data used to be, and this basically means the first packet arrives broadly 600, 700 microseconds after the beginning of the frame or field, after the PTP alignment point. And as I'll show you in a minute, some scopes don't at all make this very clear what time they're referring to. Sometimes it's hidden in a different menu, sometimes you have to expand the little window to see both of them. And I'll talk about this later, how it can go wrong. And I think it's really important to understand what you're actually measuring, because I see people say they're measuring one thing, but they're measuring timestamps, so they're measuring packet arrival times. I see people measuring packet arrival times and actually measuring the timestamps. So this is an example of one of the scopes. It's the Prism. I believe to get all of this, you have to actually expand it. You don't actually get it in its default view, which also causes a lot of confusion. So the left is the packet arrival time relative to the PTP alignment point, and the right is the RTP timestamp relative to the PTP alignment point. I must admit, speaking a bit personally, well, I'll mention that a bit later. So either of those could be wrong. Packet arrival time could be wrong relative to the PTP alignment point, or the RTP timestamp could be wrong relative to the PTP alignment point. This is the Fabrics product. Similar thing, a bit more detailed. I must admit, though, I got this wrong in its interpretation, had to read the manual. I assumed doing what I do, not reading the manual, thinking I know what I'm doing, and actually had to go and read the manual to really understand what's going on. There are multiple video timing meters available, packet arrivals and RTP offsets, and some fabrics may not actually have this option, so they may have a reduced version of the screen if they don't have the right measurement license. I mean, speaking personally, I think having had to debug these in an operational environment, both as a vendor or as a vendor going into an end user's network and trying to resolve, personally, I think the Prism is a little bit too vague and the Fabrics is a bit too complicated. And I'll show you a bit later, I'll show you in the next slide. As a result of this, we kind of had to use our own internally built tools to get these measurements over long periods of time. Because some of these measurements don't necessarily stay in the device. If that device needs to be used by someone else, you lose those measurements. So here's some example of some real senders in our lab. Our lab, for various building reasons, doesn't have roof access to get GPS. So in our lab, we pretend it's 1970. So if we look at one of the first sender here, this one is both good. It's got its first packets arrived. Well, I would clarify, I'm not Willem Vermost. I haven't done a full 2110-21 analysis. I've just done the sort of first level, first line support. Let's look at a problem we have in a facility before going into the real nuts and bolts of EBU list and 2110. So first packets arrived 0.758 milliseconds after ideal, and its RTP PTP offset is 0. It's spot on. Both are good, broadly speaking. So the second sender is interesting. Its first packets also arrived reasonably on time. Its RTP timestamp is also like okay. It's one. So the middle column shows that we're one RTP clock tick out. And here's the third sender in our lab. This one again. First packet arrival time is kind of okay, nothing terrible. Possibly a more detailed 21-21 analysis is needed, but practically probably not the end of the world. But its RTP PTP offset is bad. It's in the past. Packet arrival time is good, but RTP timestamp is bad. And in reality, it needs continual measurement in a real facility, and we see jumps happening overnight and coming back. And there are also similar measurements for audio, a bit simpler than this. Can also be very problematic sometimes of audio equipment. This is where maybe it gets a bit controversial, how I think a receiver should use timestamps. So what a receiver should do is it should take a timestamp, it should work out how many RTP wraparounds there have been from the PTP epoch, and as using that data, it can then realign its received RTP timestamp with the current PTP time and have an absolute timestamp, so essentially converting from a relative timestamp to an absolute timestamp. This sounds quite complicated, but actually ends up boiling down to 1 or 2 lines of code. If you do some modular arithmetic, they're a bit problematic if the timestamps are a bit too far forward or too far in the past. Relatively speaking, high school mathematics. And then a device can once it has gone and realigned its timestamps and has an absolute timestamp that's PTP aligned, it can therefore go and do synchronized video and audio and do what it needs to do downstream. But as you saw before, all of those sources into many devices, even the ones in red, actually work fine. And this basically proves that many of these receivers are not doing this. And we can also, in our lab, generate artificial sources with incorrect timestamps. But we see many receivers work fine. So it's pretty clear that some devices aren't using timestamps. And this is a big challenge in many ways because it allows for timestamps to just run freely in facilities and be wrong and no one notice unless they're really looking at things carefully. Or they're using a receiver which is doing full wraparound and realignment. So where and why do things go wrong? Probably the most common one operationally is when people route non-PTP locked SDI sources into encapsulators, or if that encapsulator lacks a frame synchronizer, so it can't create new frames or drop frames to be PTP aligned. So you often see packet arrival times wrong or jittery. You see attempts by the encapsulator to try and correct for this. The RTP timestamp is often bad. The fix for this is to genlock your source or enable frame sync if available. But sometimes in the field, operational requirements mean people just plug in random devices which are not genlocked and maybe low end enough not to have genlocks. So they have to go and route them into frame syncs. A bit like the old days, to be fair. Or, as in my examples, the encapsulator produces invalid RTP timestamps. Fixed offset, sometimes jumps. I've noticed, for example, some of the more US-based companies haven't tested things as rigorously in Europe and vice versa. So the US frame rates will work perfectly and the European ones may not, and vice versa. And it's quite long and challenging to investigate whether this is a transient issue, you just reboot the device, it comes back, or it's a much more complex inherent issue that you have to go back. There's also some products where you route a signal and it can take a good couple of minutes to settle down and produce a valid timestamp, so it's wrong, and it gradually drifts its timestamp back into being correct. This could also be often difficult, to be fair, for a vendor to reproduce or to explain to a vendor, because very few devices complain. So to conclude, timestamps are a really important part of 2110. Receivers need them to match audio and video. They can be hard to measure and interpret. Certainly, I've been in a facility during the pandemic. mask on, can't breathe, thinking hard, scribbling my notebook. Is my minus sign, does that mean I'm ahead of the alignment point or behind the alignment point? The maths can cause headaches. It's not simple. Timestamps are regularly often confused with packet arrival times. I often see reports where people mean one versus the other. These need to be measured continually. You can have jumps in the middle of the night that can lock you up. They can kick downstream devices out of sync, for example. But it's only maybe a couple of frames or more than a couple of or seconds in the space of, and that jump happened over a day or two. Very important to make sure encapsulators have frame syncs or all sources are gen-locked. And it's also important to understand the reasons for these invalid timestamps. There may be all sorts of reasons why. Any questions?
Okay, thank you very much. Our next presentation is all about NMOS, the wonderful control protocol that was developed in conjunction with ST2110. We have an expert speaker here, Jed Deem, the CEO of NextEra Video, and he's going to be talking about NMOS. Can there be one control system to rule them all? So welcome, Jed.
Okay, thank you, Wes. Thank you, everybody, for coming today. So I've got a bunch of material. I'll be going through probably pretty quickly, but feel free to stop me if there's something you want any more detail about. Here's the outline. So we're going to start with what is NMOS, what are the required pieces, what are some of the optional pieces that some people might want to add to their products or systems, what are the new things that are under development that we're meeting weekly to discuss in the activity groups, and why do I care about all this, and is it going okay, and finally, how can I try it myself? So let's jump right into it. So what is NMOS? Well, it stands for the Networked Media Open Specification. It was developed by a group called AMWA, the Advanced Media Workflow Association, and the intent was to deliver an open system for control of IP-based products, particularly 2110, to allow one control system for basically doing the routing. In the SDI world, remember we had a different control system for every vendor's router, but we didn't want to do that in IP. We said, let's just have one system that everybody uses. So that's, in essence, what the NMOS system does. So it allows us to seamlessly interoperate, and that's really the trick. Originally, when 2110 devices came out before the NMOS was ratified, it was a lot of typing in IP addresses and doing drivers for each specific device, and that was just very painful, very time-consuming, not really a good use of anyone's time. So we said, well, how can we make this plug and play? Well, how do we take it beyond what we had in SDI and make it plug and play and auto recognizing of devices and as easy as push button simplicity, but with the benefit of having automatic discovery, much like you have when you plug in your printer. You don't have to go into your PC and tell it what COM port you're on anymore. It finds it automatically on your network. So that's exactly what we're trying to do in NMOS. So how does it work? Well, we've got a cloud in the center, which represents our IP switch. All of our video sources are going into it, and our syncs are hanging off of it. So we've got a couple cameras on the left in this example, and we've got a monitor on the right. So what happens when you first power up the system, all the devices connect to that registry over there, which is a PC running some software and identifies themselves. Then the control panel, as soon as that happens, he can go query that registry and say, oh, I see I have two cameras here. I've got maybe a Sony and a Panasonic camera, and I've got a display, and it can even present those on the buttons if it likes. The control panel could put the name of the device that's there. So then a user says, okay, well, I want to do a route. I want to do a destination source take, just like you would in the SDI world. But a couple things happen in the background. There's a few layers of software that are involved. So first, what it does is it tells the next source, the current source to disconnect. So that X means disconnect that stream from the sender 1 to the receiver. So let's say it's already connected, and then it tells the switch through this protocol called IGMP, Internet Group Management Protocol. It says, I want to subscribe to that second camera on the lower left. So it's all done in the switch. So the receiver tells the switch, I want to listen to these streams. All these streams are coming in, blasting away at the switch, and the switch is just holding them until somebody asks for them. So that's what NMOS does. It says, please give me stream number 2, disconnect me from stream number 1. Make sense? Sound reasonable? Okay, good. Okay, well, so how does this all access? This is a control protocol we discussed. It's an API is what software people like to call it, application program interface, but really in plain English, all this is a series of HTTP commands, much like you would run in your web browser. If you browse to a website, you're doing a HTTP get of that URL, right? So in this case, if I want to read a status of an NMOS device, I do an HTTP get to the IP address of that device /xnmos/ the thing that I want to read or access, the API name. If I want to command it somehow, like to do an activation, meaning to do a switch, then I do a put, an HTTP put, which is a write to that IP address /xnmos, like I might want to write to a sender. I might want to write to an audio map. I might want to write to a secure port. So it's a very simple interface. You can do it from the command line if you like, using there's a command called curl that you could type on the command line in most Linux and Windows-based systems, and just type these commands. You can go into your web browser and browse directly to the XNMOS resource names, and you can look and see, has this device shown up on my network? Is it in the registry? You can learn a little bit about it. So pretty simple way to access it. So what is a typical implementation? Say you're a product manufacturer and you want to add NMOS and or 2110 to your device. What does that look like? Well, here's a picture of a typical product. It might be, let's say, a gateway, an SDI to IP gateway or something like that. In the lower left, it's got the 2110 FPGA cores. Most of this done in FPGA. It can be done in software, but typically it's done in FPGA. And then, that's doing the stream management. And then on the far right, you've got the PTP, which gets your timing all lined up. And the piece we're really talking about today is the upper left, the NMOS core, which is a software core that's something that our company provides in addition with the 2110 pieces. But what that allows you to do is connect commands that would come from a controller down into your FPGA hardware to tell it what to do. Tell it, I'm going to listen to this stream, or expect a stream coming in that's 1080p50, expect this kind of colorimetry. All those things would come in through all these node APIs, all these slash sources, /senders, /receivers. That's references the previous slide. This is how we tell it to do it. And then that activates the device, which is in the upper right, a camera or a graphics system or something might be sending content in or out. That allows the content to come into the FPGA and do the processing. Okay, so let's jump into, that's kind of the overview of how this all works and how it ties into 2110. So what are the required components of NMOS? First, I have to define what does required mean. Well, you probably have heard of the EBU. They actually made this document called Tech 3371 that says, here's our technology pyramid. Here are the minimum requirements for an AV over IP system. And as you can see, it's got listed all the basic NMOS pieces, the ISO 4, ISO 5, ISO 7, 8, and also ISO 9. And we'll go into detail about what all those are, but this is what I mean by required components. EBU says you should use these because it's going to make your life a lot easier. Okay, so let's start at the beginning. ISO 4, this is the first part that was developed. It's the registration and discovery. This is the plug and play piece I was talking about earlier. How does my control system know that I've got a device out there? Well, there's this language specified through ISO 4 that says, well, if I'm a node, I can talk to this thing called the node API, and I can tell it I'm a camera, I'm a monitor, this is my IP address, this is my colorimetry. If I'm the registry, which is, remember, this database sitting off to the side that's holding all this information, I've got a registration port or API, and I've got a query port or API that you can actually access from any device, from your PC, from your web browser. You could go into that query API and, again, through an HTTP read on your web browser and see all the devices that are on the network. Very handy, very, very nice for debugging a system. You don't have to run around and see who's turned on and who's actually working. So that's kind of the first step of it, is how do I register everybody on the network, put them in a database that anybody can see, a controller can see, or an operator that's trying to debug the system. Then, okay, I've got everything in my system. Now I want to do a connection, a switch, which we actually call activations in NMOS. That's what ISO 5 specifies. Here's the protocol of the command that I have to send from my controller to my sender and my receiver to say, please connect A to B. So normally it's just telling the sender, turn on your stream, and then it's telling the receiver, here's the SDP file, the session description protocol file of the sender that describes all of its capabilities. Please configure your hardware to lock to that, and then tell the switch that you want to do this IGMP join. And there's three ways we can do an activation. We can do what's called an immediate activation, which is says now, switch right now, this instant. or you can do it time-based. You can say switch it in 5 seconds, which is a relative time, or you can do an absolute, switch it 12 o'clock or 1 o'clock at the next show. So it's a nice way of automating some of the capabilities. Again, things that weren't really built into any SDI control protocol that are part of this NMOS. So that's your basics. I've registered my devices, I can switch them. Okay, and that's kind of where we started. But then we said, well, and we need to take it a little bit further. What about, tally, right? I've got IP devices. I'd like to have a replacement for the, the traditional wire-based tally system. How do I do tally over IP? Well, that's what the next one, ISO 7, does. So tally, for those of you that don't know, it's a way for your switcher to, for instance, tell your camera to light up the tally light on top that says I'm pointing this camera at a particular talent in the news set, and I've selected that camera so the news anchor knows where to look. So there's a detailed protocol here that allows us to send these events or these tally indicators over IP just as another packet using the same ISO 5 connection mechanism. And it can be done a few different ways. MQTT or WebSockets are kind of the low-level details about how that works, and there's pros and cons to each of those, but it's got mechanisms to support that GPIO over IP. Next, something else that we didn't really have in audio, in SDI rather, is audio mapping. That's ISO 8. That says, in SDI, we had to add boards to our routers, embedders and de-embedders, and we could add a bunch of extra hardware to do audio shuffling. But in IP, you don't have to do that because the video and the audio and the ancillary streams are all set separately. So you've got all your audio streams kind of bouncing around in the network. So it's not too hard to actually be able to do a channel mix. So that's what ISO 8 does, is it allows you to specify your inputs and your outputs and a map of how those connect. So I'll give you an example, make it a little bit easier. This is a demo actually we did a few years ago at NAB to show how the ISO 8 mapping works. We had a bunch of senders and receivers, and what we're trying to do is map the inputs on the left, which actually come from 2 different senders. So I've got sender 1, channel 1 through 8, and then sender 2, channel 1 through 8. So I've got 2 different audio senders out there, but I want to map those to an SDI embedded audio output, which would be the top. So I've got 16 channels in my SDI stream along the top. And what this diagonal pattern is doing, just by clicking those boxes, it's doing an invert. It's saying I want to take the last channel that comes in and put it in the first SDI output, and vice versa. So what you can see the effect is the source was this harmonic source in the upper left that had decreasing audio signals, signal strength from 2 sources going diagonally down, and then our output, the Nextera gateway demonstration box on the right, which has it inverted the other way. So it provided the ability to map any input to any output. So nice little feature that we didn't have automatically in SDI. It doesn't cost you any more wires. It's just an extra layer of software. Okay, and the other nice thing that NMOS brings is this ISO 9, which is the system resource. When you start deploying 2110 systems, you quickly realize there's a lot of information that has to be entered into to each product. You have to tell every single product what the PTP domain is. That's not fun. If you've got 100 or 200 or 500 different products, you have to go in manually and type that information in the old days before NMOS. Well, now with NMOS, we're saying, well, why don't we take this information that has to be, that every device needs to be told, and we'll just put it in a little system resource, a little database. We'll have just a little program running on a PC somewhere that holds things like the PTP domain, the heartbeat intervals, like where do I want my syslogs located, for instance, for storing debug information. What protocol am I running? Am I running secure? Am I running non-secure? These kinds of things. And one other cool thing is this thing called system ID, because you can imagine if you have a node, a product, let's say a gateway or a server, it's in one IP system and the power goes down and the power comes up, what do you want to do? Well, normally you want to wake up the way you went to sleep. If you're transmitting a stream, you want to keep transmitting. But what if that box was powered down and moved to a different system and powered up? you don't want to be transmitting again. You're in a totally new system. You don't want to be flooding the network. So what it does is it sees every device looks at this as, well, my system ID is 17. It stores it in some non-volatile memory. It goes to sleep. It wakes up. What's my current system ID? Oh, it's still 17? Great. I'll wake up the way I went to sleep. I'll start transmitting. Oh, but now I'm in system 23. That's a different system. Okay, I'm going to turn off my transmitter, or I might do a factory reset. You have a couple options. So it's a convenient way, again, to try to give you a little more plug and play and ease of moving systems around. So those are the required components. That's what every NMOS system, according to the EBU, should really have to actually make this work. What are some of the optional components? Let's jump into those. One of them is ISO 6. I won't talk too much about this, but this is just a different way of doing switching instead of IGMP. It's using SDN, software-defined networking, where the switch is actually being programmed by the controller to switch a stream to a different destination, whereas in our typical system, IGMP, it's the receiver that's asking the switch for a stream. So this never really caught on because it turns out IGMP can handle thousands of streams, so you don't really necessarily need this. It's some extra complexity. It does give you a lot more control. So if you're willing to absorb a little more complexity and you want to be able to have complete maps of your system and you want to do bandwidth reservation, it's kind of a nice thing to have. Topology, discovery, those things, but most systems just rely on traditional IGMP. So this is kind of an illustration of that. In the IGMP world, it's the receiver that's asking for the connection, whereas in the ISO 6 world, it's the control system, the NMOS controller that's telling the switch to do the connection. Okay, then we have this other thing. There's a bunch of these BCPs, these best current practices that are part of the NMOS library of specs that just make life a little bit easier. This one, 002, is called grouping, and that allows you to say, well, since I have separate audio, video, and ancillary as 3 separate streams, it'd be nice if I could tie those together logically and say, well, these are all coming from server 1. So that's really what this does, and it's a common, so you could name this, right? You could name these groups. So I have a group called Playout Master that's got a video, audio 1, and audio 2. And you could also have these things called roles. So I could have a role of primary or 2-channel audio or 6-channel audio. It's just kind of a nice thing that you can set in every node. You can define these groups that when your controller connects to you or looks at your registry entry, it can see this and it can present it to the user. And it can just give you like one button to route video, audio, and ancillary for that whole selection. Okay, let's talk a little bit about security. So, as you move to IP, that's always the first thing that an end customer starts to worry about. How do I protect my content? How do I protect my distribution system from bad actors that are trying to do things I don't want to do? So the NMOS security group came up with a bunch of goals, talking to a lot of end users, like what are you looking for? What are the things that are important? So, one is confidentiality. How do we make sure that the data passing from A to B is unreadable by other third parties? 2 is identification, which makes sure that the API knows it's acting with a trusted authority. 3rd is the integrity. Make sure that the data traveling from A to B hasn't been tampered with. And finally is authentication, that makes sure that packets going from one API are coming from the API that expects and not from somebody else. So how do we implement this in NMOS? Well, there's a bunch of these BCPs, 003-123. Number 1, I would say, is the most important because it solves the first problem of taking the communication from the unsecure mode to the secure mode. Much like your web browser, you notice most websites now are HTTPS. If you have one that's not, you get a nasty warning in your browser saying this site is unsecure. Well, that's what this is doing for NMOS. It's saying, let's not just do an HTTP put or get, let's do an HTTPS put or get. So now it's encrypted going from A to B, so someone in the middle can't be listening in. If you don't have a certificate, you can't actually issue a put or get. So that's the most important one, and that we actually just did interop testing of that at the JTN-NM event 2 weeks ago, and that's looking really good. We've already got solutions available for that. If you want to take it a step further, you can do authorization, which is 00302. So, first remember, authentication is, am I a legitimate device that's allowed to talk to this other device? The second is authentication. Me as a user, I'm logged in. Do I have permissions to do a particular thing? So that's the authorization. And then the final one is certificate provisioning, which is because certificates sometimes can be a pain to distribute. So we've come up with a way to do automated certificate distribution so that you've got trusted sources. Okay, and then we have IS10, which kind of ties this all together with this authorization built around some industry standard techniques like JSON web tokens and this OAuth authentication system. So let me just step back a little bit and talk about the underlying structure of how this all is protected. It's a system called PKI, Public Key Infrastructure, and the way PKI works is you've got a way where you can provide these keys, public keys and private keys, to protect data, and this is the way web traffic is protected, and this is the way secure NMOS is protected. So let's say Bob would like to send a secure message to Alice. Bob would encrypt that information with Alice's public key. So this is a key that she just openly can distribute. That's fine. Anybody can see it. So if you want to send Alice a message, you encrypt it with her public key. Great. But she's the only one that can decrypt it because she protects her private key. She's the only one that can see that, so she can send those messages through. That's the same way that's the way basically HTTPS works. So that's a lot of talking about how it works. Let's just show you a picture. It's a little bit easier to absorb. So I've got a broadcast controller. I've got a source and a destination. I want to send securely. I want to command data to go from the source to the destination. Well, there's one new piece added to the system called this authorization server. Again, it's another PC or the same PC running another piece of software. And the way it works is the controller, your button panel or whatever your control system is, before it tries to do this activation, it says, hey, Mr. Authorization Server, I have user 1 that wants to do this thing. It's a request. Can I do it? And he comes back and says, yes, they're a valid user. They're authorized to do that particular switch that you've asked for. So he sends back this token, this JWT token. And then the controller uses that token to tell the source to start transmitting. Source says, well, wait a minute, I don't know, how do I know that's a good token? Let me compare it against the public key of the authorization server. Okay, yes, that's a good token. I'm going to start transmitting. Transmits it to the switch. Again, it stops at the switch until somebody asks for it. Now the controller tells the destination, hey, here's the same JWT token. Please subscribe to this source stream. He says, wait a minute, is that legit? Yes, it is. I compared it against a public key. Great. Now it all happens. So this is a question. Yes, sir. The switch isn't drawn in here. Yes, sir. Yes, the traffic all goes over the switch. That's what I was trying to show with this little half arrow here. The arrow stops at the switch, and then when you subscribe to it, then the switch lets it through. Okay, I should probably put the switch in to make this more clear. Thank you. Okay, so this is just a slide that lists a bunch of these secure technologies. I won't review these. These will be in the recording if anybody wants to look at them. These are all the cipher suites that NMOS uses, different levels of encryption. This is, again, just a reference. It'll be in the recording if someone wants to see what all these acronyms mean. So let's talk a little bit about the future and kind of come back to the title of the presentation. Can there be one control system to rule them all? Because what we've talked about so far is really just basic switching control, not device control. Just, it's just routing. So, so how do we take it a little bit further? Well, the first way to extend NMOS is to be able to handle different types of content. So in this case, JPEG XS. So JPEG XS is used sometimes to compress 4K to get it into 10 gig. It's used in the Pro AV market to compress it all the way down to 1 gig. The controller kind of needs to know that, right? If you're going to try to route one sender to one receiver, it needs to know if they're compatible with each other. So that's what this BCP006 does, is allows you to present information about each individual device. I'm either RAW or JXSV, JPEG XS video, are the two common options, but they could also be other codecs. And it just uses all the other fundamentals that we built upon, that we talked about, ISO 4 and ISO 5, and updates to the SDP file to make this happen. The next one is stream compatibility management. How do we do things like in the HDMI world, we have EDID, which says, Mr. Monitor, what resolutions do you support? And let me advertise those to the rest of the world so that I'm not trying to send you a stream that you're not compatible with. So we're doing the same thing in IP. We're allowing you to advertise to the registry the formats that a receiver supports. And that could be dependent on the display that it's connected to, right? Maybe a receiver can handle 50 hertz and 60 hertz, but the display can only handle 60. So, you can actually use the EDID capabilities to look at the display and then advertise those using this BCP004 receiver capabilities mechanism. Again, these are just other APIs. This is just a place that you could browse to with your web browser, or the controller can browse to and read a little data file that says, hey, here's what I'm capable of. Here's my video format, my frame rate, my color sampling, my SDR, HDR capabilities. And then this BCP005 specifies how I can map my EDID information into that. So nice little handy piece. So here's kind of the where this is all going long term is IS-12. How do I go beyond just informing switching and be able to actually control a device? Because you've got now one API. It's nice that it's one common API for switching, but every device I need to talk to, my control system needs a driver for. I need to talk to a camera or a graphics unit or a switcher. Everybody has their own control protocol. Well, why not have a universal protocol? And there's a lot more work to do to make this happen, but that's really the goal here, is a common protocol so that any device will speak this same language, this NMOS device protocol language. And so it's intended to be a replacement for some of the commonly attempted ways to do this, like SNMP was a first attempt. It's just very difficult to add new MIBs, so that's probably not going to last much longer. OpenConfig was another attempt, but the scope wasn't quite wide enough. Ember Plus, again, another great approach, but it's not 100% open. So let's build a 100% open solution and have templates for talking to every type of device that's out there. So quite a bit more work to do, but this is some work that's well underway. It's over a year of effort's gone into that. There's a lot of data in these references at the bottom. These are all available on the AMWA GitHub, by the way, if you want to read some more about these. So the next thing to do is develop all these block specifications for the different types of products. All the protocol stuff has been worked out. Okay, so why should I care about all this? Well, manual device provisioning with typing in a bunch of cryptic IP addresses is just a pain. Nobody wants to do that. It's very error-prone, time-consuming. Plug and play is fun, right? Press the easy button. Let's do it. Let's use a proven technique that makes provisioning new systems much easier. Most all new facilities are specifying NMOS. Most control system providers are fully supporting it. There's one or two laggards, but they're coming around. I've seen some announcements. So, NMOS is what's in most new tenders. How's it going? Well, there were some growing pains early on, and they were due to a variety of reasons. Not all devices supported NMOS early on. They didn't all get through JTNM testing because that was postponed due to COVID, and the controller specs weren't really clear, and there were no real good interop testing. But that's all been fixed now. The mitigation is we do now have JTM testing. It's back. We have controller testing. We just did face-to-face event at Riedel a couple of weeks ago. We've got this new implementation guide for NMOS controllers and lots of automated tests. So We believe our growing pains are behind us. It's still a lot better than manually setting everything up, but we're definitely getting there. There's testing tools available. I'm running out of time, so I'll go through these pretty quickly, but you can look at the slides later on. You can see links to the Easy NMOS container, which has registries. You can run the testing tools. If you're a product developer, you can run all these tests yourselves, validate your product. You can download Riedel NMOS Explorer, and you can look at your network. And you can see all your sources and your senders and receivers and devices and drag them around. It's a little cryptic, but it works. If you want something a little fancier, Matrox has got a new system called Conduct IP that's a little more plug and play and drag and drop and auto discovers. And this is what we're showing at our booth, by the way. You can come over in Hall 10 and take a look at what we're showing. It's got all the senders on the top and the receivers on the left and normal XY matrix, and we can show you how quickly NMOS routes things back and forth. So takeaways, NMOS is here to stay. It's solid, it's stable, it's mature. Control systems have greatly improved thanks to the interop testing. Some of these new features like ISO 8 audio mapping, system discovery, grouping really take NMOS to a new level, way beyond what SDI could ever do. And now the security is filling a much needed void in the industry to allow us to have secure connections. And finally, NMOS is being extended to be more of the universal control system that it can be. So one ring to rule them all, one API to rule them all. Okay, yeah, so the question is, I'll paraphrase a little bit. How complex would a product implementation need to be to support this NMOS protocol? So it's not too bad. You do need an embedded processor. Usually it's an embedded Linux processor, but it can be a ARM built into an FPGA, or it can be a separate ARM device. The software is relatively lightweight. It doesn't require a lot of processing power. It's actually being done quite often on embedded soft processors like microblazes or NIOS processors. So it doesn't need a gigahertz processor. It needs a couple hundred megahertz processor. But you do have to have some sort of embedded Linux on each device so that it can respond to these requests. So, okay, thank you.
Thank you, Jet.
Yep.
Our next presenter is Tim Hall from Mac Media, and he's here to talk about NMOS at scale. So take it away, Tim.
Good morning. Firstly, apologies, I'm not the build speaker, but secondly, congratulations for finding the room. Took me a while. So what I'm here to talk about, who am I, why am I here? So I'm based in the UK. I'm now a consultant, but I used to do some real work when I used to mix audio. I then went into system design, station builds, always thinking about workflow control, never forgetting the audio, so intercom's always a big part of what I get involved in. I've now been a part of several IP projects with many different technology stacks. We started with 2022-6. We've done a lot of 2110, AS67, and some Dante along the way. And as I say, a mixture of control and orchestration and technology stacks as part of that. So what am I going to talk about? Well, I'm going to talk about a real-world implementation that I'm still involved with, what are the issues that we found along the way, and how might we improve matters. So you can read this on the NMOS website. This is just some highlights of what NMOS sets out to do. Largely, it does. But I'm going to concentrate really on the last 2 bullet points about finding, connecting, configuring, and how well does it scale. As I said, I'm going to talk about real-world implementation. We've got 30+ vendors across multiple sites, 2 large data centers housing the back-end processing, mixture of NMOS and native API control, and some 300,000 senders or receivers, senders and receivers combined. A third of those are NMOS. That's quite good. From the previous project I did, where we had 4 devices that were NMOS, as in 4 instances of one thing sitting in an MCR. So you know, we've achieved a lot with NMOS. We've got a little bit of a constraint. The vendor that's doing the orchestration isn't using a registry. That means we need to go and discover every device ourselves. That's proved to have added somewhat of a configuration burden, but it does give us very tight control on letting things onto the network. So in order to make it work, we've had to create an offline data model and the tools to gather, process, and prepare configuration for the devices that we're going to control, the orchestration engine itself, and the higher level control system. It's given us a single point of good data that can then be reused for different uses. So, some more constraints. Our orchestration layer GUI only displays a single label for an object. You've got to drill down if you want to find out more stuff. And that label in NMOS terms is inherited from ISO 4. We can override it, but the big problem is when you're adding lots and lots of items, how do you actually figure out what's what? And I'll come back to some examples of how labels can be really confusing. Our orchestration layer is not using logical grouping. The sheer amount of data makes navigation through the system hard, very hard. Finding stuff is difficult. The concept of having 2 data centers gave us some geographical resilience, but in order to make the workflow and the operation work, yes, they're separate, but they need to be interlinked at a certain level so that we can make use of resources that sit in both of those data centers. This may sound like a silly thing. The higher level control system uses an integer-based model for dealing with routers, because it still thinks about routers. Well, the world's moved on. We don't use integers anymore. We use GUIDs. I guess another constraint, it's an extremely long project. We've been going 3 years and we're now on air and we're still growing the system. Okay, so some of the issues we found. As I've said before, troubleshooting gets challenging using native ISO 4 labels, especially when those labels are in a mixture of formats and presentations. Not all vendors using natural grouping, so there aren't many clues from looking at raw ISO 4 information to figure out, okay, you've got this thing and it's got some devices and it's got some senders, but how are they linked together? I don't know, because your labeling is weird and you're not using logical grouping. Some NMOS implementations make it difficult to distinguish between instances of a given device type. What do I mean by that? Well, if I plug 20 CCUs in and they all say, hi, I'm a CCU, well, which one's which? Oh, well, yeah, but I'll tack on the serial number. Yeah, okay. Our project has been going 3 years. That means 2 of those years we were configuring it remotely. Not so easy to go and look for the serial number when you are 200 miles away. So large-scale implementations take time. We need clues to help us identify individual things and items, groupings, to ease our configuration burden. Another issue we found, and this is a regular occurrence, when a GUID changes, for whatever reason, it's quite difficult to replace that object because that's the primary key for that object. Well, when one GUID changes, it's difficult. 100 GUIDs change, yeah, even more difficult. So, yeah, not good. When I'm modeling a new device, we fire that device up. I point some of my tools at that device and find out, okay, well, it says it's got one node and it's got 3 devices, and each device has got some senders and receivers. Well, that's how it is at the point in time that I'm looking at it, but I have no idea what will happen if I change the running mode of that device from a UHD personality to an HD personality. I have no idea what's going to happen if I update to the latest firmware. The vendors don't really help me. They don't give me a sheet which says, this is the structure we use, and this is the structure, how the structure might change if you change the mode of the device. And completely coincidentally, last week, we're about to bring on a new device. The vendor sent me a sheet which explained exactly that, exactly what I've been asking for. And I didn't even prompt them. GUIDs. GUIDs change. Okay, so there's 2 issues we've had with GUIDs. One, non-unique GUIDs. Well, it's not a GUID. Okay, it really just upsets my OCD when they're not unique. When I'm saying not unique, what we've seen is reuse of a given GUID on a different instance of the same device. It just looks odd, especially when these GUIDs are sequential. Again, they're not really unique, not really guaranteed unique. So it's not much of a problem if they're not unique within themselves. Obviously, when you fully qualify them, it has to be unique. But one of the biggest issues we found are non-persistent GUIDs. I reboot a device or I upgrade its firmware. Oh, look, all the GUIDs have changed. Worse than that is if I reconfigure the device and all the GUIDs change, because that reconfiguration might be an operational reconfiguration that jumps from UHD to HD. It's particularly been an issue with audio devices. So, labeling schemas. So, in my head, we've got 3 different ways of labeling things. So here's some examples of senders or receivers that are fully defined by the vendor. So what does the first one mean? It means nothing. I can't work out what that really means unless I've got a lot of knowledge of the device that's sending it. And in that particular case, that label isn't unique. It might change if I reconfigure that device. Second one's, okay, slightly easier. I can see what it is. It's going to receive some video, and that looks like it might have a bit of serial number in it, so that might give me a clue, but I've still got to go and find out what that is. So here's one that's partially vendor defined. So the first bit, this bit here, I've defined. The last bit, what on earth does that mean? No idea. Trial and error. Spent a good couple of hours trying to work out which one was which, and then found out that different versions of firmware had different types of label on the same cards in the same device. Customer defined. Well, that doesn't offend my OCD because that's nice and uniform, and it sort of tells a story. For customer defined labels, they're generally three different ways of allowing the customer to do that. So the vendor will allow you to type them directly into the config tool. Okay, if I'm typing in 5, that's not a problem. If I'm typing in 500, I don't want to do that, thank you. Maybe there's an API, that would be good. Maybe I create a pattern and say, well, okay, I know you've got 100 audio senders, let's use this pattern with placeholders. Or I could upload a lookup table. Some of the devices that we've seen running on software, I can just post a JSON file into the device's file system, and I've created a lookup table. So now, when I look at NMOS data, I can actually see some labels that mean something to me. So our vocabulary that we've chosen, this is our solution. This is not something we're advocating to be a fixed vocabulary. We're saying this suits our purpose. So every object in our design, whether it be a physical thing or a logical thing, so it might be an example here is a camera control unit. It could be a server, it could be a sound mixing desk. We give it a code, which we call a unique ID. Where it is, that's 5 digits. What it is, it's a CCU. And which CCU is it? Oh, it's 1, it's the first one. Doesn't mean it's camera 1 in any particular control room. It's just the first CCU in our infrastructure. So this gives us a context for every object in the design. And in fact, those UIDs appear on AutoCAD schematics. They appear in IP address tables. They are our way, our shorthand of knowing which object we're talking about. Usually, not always, the device gets that name. We can put that UID into the device, and it becomes the ISO4 node label. But not always, because sometimes there's some restrictions on the characters that we can use. Now, maybe you might argue that we shouldn't have put slashes in our unique IDs, but we didn't know what we didn't know when we started, and you're probably right, we wouldn't have. But that physical or logical device might have several nodes, so we might need further qualification to say, well, actually, this is #1, #2, #3 of our CCU 001. So then, for senders and receivers, we've mandated the format of the sender and receiver text using a shorthand of essentially recreating the logical grouping, but in a label. So if you think of it as spigots, yeah, we're still thinking about what we'd have if we had SDI and a baseband handoff. So spigot 1, that's logical grouping. Everything that says SO1 is related within within our IP system. And then for the essences, we've just chosen some labels, some letters that mean things, you know, video, audio, metadata, X for JPEG XS. So this is really a plea to vendors to say, as an implementer, what I really need is a clear definition of what your node device sender receiver schema is and how that might change at runtime. Please implement natural grouping. Okay, natural grouping is not mandatory, but it's a pain if it's not there. And at least one of the systems that I've been working with in the last 3 years, it becomes incredibly difficult if natural grouping isn't available. We've made some progress. The Wuppertal JT&M tested event that took place earlier this year tested 74 nodes, 65 of those passed with regard to the natural grouping. But that's still only 2/3. So again, change the GUIDs when really it's only when it's necessary. Don't change them just because it really makes implementers' life difficult. And give implementers the opportunity and tools to choose a labeling schema that fits their project facility. I've given one example. You don't need to do that. It was our way of providing a unified approach when we go to the orchestration layer so that everybody has the same vocabulary. This is the very thing, the very flow that we can all talk about in the same way. And that makes troubleshooting much easier. So that's my plea to vendors. So what's happening within AMWA? We're discussing how we might encourage or enforce some of these things within implementations. As a first step, we've worked up some user stories which try and set the stage for how a piece of work might be able to deliver some tangible results. So at that high level, I just need a clearer way of differentiating between objects that appear in the tree. Because when we leave vendors to decide, there's just too much ambiguity. That's me. Any questions?
Okay.
That's super. Excellent.
All right. Nice. Thanks for bringing us some. Thanks for bringing us some real-world experience there, Tim.
That's okay.
Appreciate it, and be happy to have you join us for the rest. Okay. Thank you.
Thank you.
Right. Okay, good morning, everybody. Our next presentation is starting to get into some of the technologies that are going to be used to support IP media networking systems, including network design, best practices, particularly ones for SMTPE ST2110. So we have Nemanja Kamenica, the technical marketing engineer from Cisco, here to talk about Cisco's vision for putting together an ST2110 media network. Welcome, Nemanja.
Thank you, Wes. Hello, everybody. So, as Wes said, my name is Nemanja Kamenica. I'm technical marketing engineer at Cisco. I've been working at Cisco for about 9 years and dealing with IP broadcast system or transition from SDI to IP on the broadcast systems for about 6 years now. So I wanted to share some of the best practices and designs, like how you can design this 2110 networks for your use case and so on. So what I have on agenda for today, just briefly touch that why you should migrate from SDI into IP, how to build a fabric, so provide you different design options, and then visibility options, because when you build that IP fabric, there could be a lot of unknown and a lot of stuff which you might not have seen before, especially if you're coming from the broadcast world. So this might be of use and having more visibility. And then time synchronization, as you know, PTP is very important, and synchronizing all the endpoints is very important. So let's look at some best practices from that perspective. So all of you must be familiar with what's on the left side. It's a SMB connector, but on the right side, it's a UTP cable. So Ethernet cable, which you probably a bunch of you have at home. So similarly, how this cable at your home can do multiple browsers, can do YouTube, can do Netflix or anything else to watch video, that's how in broadcast environment can carry multiple signals. So that's advantage of it. It's very flexible and can do a lot of stuff in the, I would say, more efficient way than SDI. So what are the benefits of the IP? So bidirectional communication. So you can send and receive signal at the same time on the same link. You don't need multiple connections to do so. Multiple signals per that connection. So you can carry video, audio, closed caption, or even multiple videos over the same link. So that's another benefit. As I said, video, audio, metadata, closed caption, anything else which you want to send, you can do over that Ethernet and over single connection as well. Ethernet, it's format agnostic, so you can carry 2110, 2022-6, and any other information, even unicast information from your IP storage can be carried over the same Ethernet connection. And it's intelligent and flexible, and I'll show you what I mean by that in next couple of slides. So where you are today, or some of you might be somewhere in between, but basically this was a starting point a couple of years back. You had a video router interconnecting all of those endpoints. So those could be cameras, microphone, video service, graphic systems, controllers, playouts, everything else over single device and over that single virtual router. And what its idea when you migrate to IP is that you just replace that SDI router, video router, and you put something which is IP fabric in there. And your look and feel stays the same. So whatever you have done before, you perform that same operation again, not knowing that something has changed underneath. So that's kind of the idea. However, the challenge with IP is that IP could be complex. And over here I have something which is called OSI model, which has 7 layers of it. And you can see that there is multiple application, multiple layers which are using that. But do you really need to know all of them? In reality, no. So what you need to know when you're migrating to IP is layer 2 and layer 3, possibly layer 4 too, but these two are kind of most important, layer 2 and layer 3. What are devices or what are the networks on those 2 layers? On the layer 2, we have switches, layer 2 switches. And on the layer 3, we have routers. So they are able to route the traffic. So let's look at challenges which are occurring on the layer 2. So first of all, you have something which is called flooding. So every time when you don't know where the destination is for that layer 2 traffic, the system will flood. Which means I will send to everybody this packet, no matter if they ask for it or no. And if you have a lot of that traffic, I'm going to overwhelm the network, so I will not be able to maybe provide some other services to that network, which is undesirable behavior for sure. The other thing is when you create an IP network, you need to take care of the loops. So you cannot have loops in your network, as they can lead into undesirable behavior where they can bring the whole network down by sending a lot of traffic or simply overwhelming that network devices so they come down. So you want to avoid that at all costs. On the layer 2, you use protocol which is called spanning tree, which mitigates loop. How does spanning tree mitigate loop? But basically observing the loop and suspending one link in that loop. Or let's say that you have a triangle, you will suspend one side of the triangle so that packet cannot create a loop. What that means is that you cannot use that links at all as they are suspended, so you're reducing the bandwidth present in the network, which is again undesirable behavior for the broadcast networking to mitigate it this way. So building the network on the layer 2, it's not desirable behavior, and I would discourage you to go even that way. Because of these reasons, flooding and basically suspending the bandwidth which is present into the network. So how you should build the network using layer 3, because you route that traffic. So you forward the traffic based on information in the layer 3 header, so-called IP addresses. Either that's unicast or the multicast. So it's very deterministic. So I know that I need to forward this particular information or this particular packet to a certain destination, which is written there. So I know where I need to forward that packet. So in this example, I have camera bottom on the bottom left, and that camera is sending information to all these 3 receivers. So I know I'm going to send it to access switch, from the access switch to the spine switch, and then spine switch will replicate to all of the leaves. And basically all those receivers, all those video screens will receive that particular packet. I avoid loops by using TTL, so I'm not suspending the link. All the full bandwidth is present into the system. So all those challenges which you had on the layer 2, they're mitigated on the layer 3. So you don't need to worry about those. And they're built into the protocol. So they're there by default. What you need to know, set of protocols which are needed for the layer 3 to work is PIM, protocol independent multicast. So that's the way for you to forward that multicast packets or find the destination for that multicast packet, or in reality find the source. You need to have some kind of unicast protocol which runs, which helps that multicast being propagated. So that's as well. And then you need IGMP to signal where is that receiver. So from that perspective, it's again another protocol. But basically these 3 by default should give you all that you need to forward that multicast traffic on the layer 3 from source to destination. So that's why we pick layer 3. When we design the network, there are 2 deployment options. So on the left side, we have something which is called spine and leaf deployment. So you have access aggregation layer. You have 2 layers of the traffic. You can connect endpoints only to that access layer, to the bottom layer, to the leaves, or you can connect them both to the leaves and the spines. So you have that option. What is the benefit of the spine and leaf architecture is that it's distributed and it's scalable. What I mean by that is that if you need additional endpoints, you can always add another leaf to this network. If you need a lot of endpoints and you need to expand a lot, you might need to change spines so you accommodate more leaves to be connected. But in reality, it's very flexible to expand and do that. From that perspective, scalable as well. Other deployment, it's something which we call monolithic deployment. It's a single chassis, single switch, presumably modular with a lot of ports. So what is the benefit of this deployment is that it's simple, so you don't need to go and search where to connect all those stuff. Routing traffic or forwarding traffic, it's very simple because you have single device to forward traffic. So it's simple and centralized. One device does everything. So those are two deployment options. I'm going to focus a little bit more on the spine and leaf architecture, simply because I feel that there could be more challenges which need to solution or requiring solution. So that's why I'm focusing there a little bit more in this presentation. So when you build spine and leaf network, I mentioned a couple of protocols, but there is a behavior which may occur in those kind of networks. It can occur in both layer 2 and layer 3, but let's look at this from layer 3 perspective. So in this case, what we have, on the bottom left, you have like a little agenda over here. So we have a video stream of 12 gig. We have audio stream of 1 megabit, and we have closed caption of 100 kilobytes. And then on the bottom left leaf here, we have 4 senders, each of them originating all these 3 types of traffic. We have 3 40 gig links going from the leaf to the spine, as well 3 40 gig links going from spine to the leaf on the right side. So there is 120 gig of bandwidth, plenty of bandwidth to forward all these 4 video streams and all these streams from all these senders. But let's see what's happening when hashing doesn't do the work very well. So we have receiver 1 receiving group from source 1. And what happens here? The receiver signalizes, hey, I need to receive this traffic. The traffic is stitched or provisioned through the network. So the leaf 1 uses the most left link to send that traffic, and then the spine to communicate to leaf 2 uses the most right link to forward that traffic. So we have 12 gig of traffic, 1 megabit, and then 100 kilobyte per link. So far, so good. Second stream comes online, or second receiver comes online, and second stream starts be provisioned. We again stitch that video flow over that same link. So now we have 24 gig utilized on a 40 gig link. Third stream comes online, or third receiver comes online. Our initial leaf and spine again put that video flow over that same link. Reason is they all carry similar multicast group, similar source, so they might be hashed over the same link. So right now we are using 36 gigabyte on 40 gig link. We are still good, we still forward all the traffic, but when the fourth stream comes online, we are utilizing, what, 48 gigabits of traffic on a 40 gig link. So we are dropping 8 gigabits of traffic. So we are basically harming all of the streams present on this link simply because hash is inefficient. It's inefficient in a way that doesn't understand that there is bandwidth of the stream as well as bandwidth of the link. So as such, will do based on the information which possess, which might be inefficient in this case. So what we need to do, we need to improve, or we need to provide some kind of intelligence so those streams can be stitched or provisioned efficiently. So how do we do this? And I'm going to illustrate something to you over here. So right now, we have the same network, but our spine and leaves do know how much of the bandwidth we have per link, as well as how much of the bandwidth we have per flow. So how that looks like, when first receiver comes, we put that flow in, doesn't matter which link. So in this case, we put again on the same links as before. But when the second stream comes, we know that our left or most right link are utilized the most. So they carry 12 gig of traffic. So I'm not going to put the next video stream on that same link. I'm going to pick another link which is least utilized, which is the most internal or most right link or most left link on the picture. So you get from the picture what I'm trying to say here. And then when the next stream comes, we put it on the middle link between. So we have kind of equal utilization on all 3 links at this point in time. And when the fourth stream comes, we again put it on the link. However, we are able to forward all these 4 streams or all these 4 senders to all 4 receivers without dropping any traffic. So why? because we know how much of the bandwidth is present on the particular link, how much of the bandwidth each flow utilized, so we are able to do this in intelligent and efficient way to forward this traffic, and hash doesn't provide any input in this case. So from that perspective, it's beneficial. So when we talk about Cisco deployments, there are two types of deployments. The first is NBM active, non-blocking multicast in active mode, which is on the left, and that's what we utilize in the first, in the example which I showed you before. So switchers are the one which understand how much of the bandwidth is present in the system, how much of the bandwidth each flow carries, and is able to do that calculation in provisioning in this way. So this is done using the same traditional protocols, PIM and NBM, where PIM is proven to, PIM as a traditional protocol, PIM is encouraged or enriched with NBM by having that bandwidth information. Another mode to this network, to run this network, it's in passive mode. So in this case, network doesn't do anything, but there is an SDN controller, which has at the same time could be a broadcast controller, which using set of APIs can provision the network in efficient way, so you don't block any of the links and you provision the traffic in most efficient way. So that's another way to create this network. So that SDN controller, broadcast controller per se, is able to have that information about the bandwidth of the links as well as the flows to provision the network. Just to kind of look a little bit further in each of these modes, in NBM active mode, we have two modes to kind of signalize if there is particular receiver interested in particular group. So on the left side, we use IGMP to signalize from the receiver to the leaf that there is particular interest for the flow, where we use, or broadcast controller uses ISO5 protocol to signal to the broadcast to the endpoint device, and that endpoint device signalize IGMP. In the second example, which I have on the right, what we do, that broadcast controller uses ISO5 to signalize to the receiver, but as well uses the NBM API to signal to the switch that receiver is present on the particular port. So just the different ways to signalize that there is a receiver, but all the flow stitching, it happens inside of the network. So there is no other influence that having a source and having signalizing that there is a destination. In NBM passive, so in this case, we have broadcast controller taking control over the whole network, which includes endpoints and the switches itself. So there is a set of APIs which are exposed on the switches itself, where that configuration is pushed, so you know where sender is and where receiver is, and the network just follows that path, that instructions. There is no CLI exposed, so you cannot go to the switch and tell it to do this. You simply have to do through a controller which basically uses those APIs. Simply you have a single place where you can absorb all that configuration. So those are deployment options: spine leaf, monolithic architecture. If you go spine and leaf, you need to manage the bandwidth, and I showed you kind of a couple of ways how to do that. But you need to also have a visibility inside of that fabric. So what I have here is Cisco's Nexus Dashboard Fabric Controller, which can visualize the network. So in the picture on the left, you see topology view. So there are two spines, two leaves, some set of multicast flows and hosts, which are present in the network. And then on the right picture, the right diagram, you see multicast flow visibility. So you see who is the sender, the device on the left, and then the multi-viewer, it's receiver. And you see each of those devices and each of the link in the network where that particular flow utilizes to forward that particular stream. So you get clear view, you exactly know what path that particular stream has taken by visualizing that. Also, what we do with NDFC, Nexus Dashboard Fabric Controller, it's RTP flow monitor. So we are able to look at sequence number of each of RTP flows. And if any of the sequence number, if there is any out of orders in the sequence, we are able to mitigate and flag those. So in this case, you see in the diagram, there are two sender and receiver, and we have found that there is missing packets on the spine and the leaf. So somewhere on the pad between camera and the spine, some drops have occurred, and we are missing some of RTP packets. So this visualization of that flow as well as the drops, it's present in this diagram. Another important thing is PTP, so time synchronization in the system. So you're able to kind of monitor that and visualize that as well, So in the top diagram, you see the correction and mean pad delay. So you're able to kind of look at those and figure out if there is any errors there. And on the bottom diagram, you see a topology where you see active senders roles in the fabric, so master or slave, as well as if there is a grandmaster in the system, it's visualized there. So you're having a clear picture of what's going on in topology, as well as how particular device performs when it comes to PTP. So all these options, visualization options, which I have shown you here, you have a set of telemetry and APIs which you can collect and expose that. So you can see those in Nexus Dashboard Fabric Controller as shown here, but you can also create your own third-party tool which will collect this information and display it in some other way per se, which will fit more your use case in a better way. It's just open, transparent, so you can use that as well. And then I mentioned PTP a moment ago. I just want to kind of tell you a little bit about the implementation in the spine and leaf architectures for SMTPE. So you should run all the network devices, or at least the switches, in the boundary clock mode. Reason is you get the better scalability and better efficiency. So what that means when you run it in boundary mode, you form master-slave relationship in each of the layer in the network. So if you look at the diagram, a grandmaster, it's obviously a master, but the next device, it's a slave on that particular link. And then from boundary clock on that particular network device to the leaves, you also form a master-slave connection. So you are able to scale more and provide more efficient time points. Use the PTP profiles, which are accommodating the deployment which you want. So either SMT2110, so SMT2059, or if those are audio deployment, then you maybe go to AS67. Treat Grandmaster as any other device in the network, so you can connect it to the leaf or to spine. In my case, I did connect it in this diagram to the spine, but as well can be connected to the leaf. And also, when you create this network, configure those slave devices to those endpoint devices in a master mode, so they cannot overtake the time synchronization part or time in the network. You force them to always work like those ports to be in a master mode, so they are slave devices. So just to sum up, use layer 3 to build deterministic network and scalable fabric. So forward based on the IP, and you mitigate all the issues which are occurring on the layer 2. Choose between available options. So either network does that control of the bandwidth, or the broadcast controller does as the end controller. Design PTP network in the boundary clock mode, so you're having more efficient and scalable way, and monitor your networks using monitor PTP or leverage some advanced capabilities present in the network. So if you have any questions, please let me know.
All right, do we have any questions? Okay, thank you very much, Nemanja.
Thank you.
Okay, appreciate it.